Pardon me, I'm a little sick. It's only partially alcohol induced. So for those of you who don't know me, I'm Egypt. I'm not the country. Um, I have a beard, but I've never used it to overthrow a country. I work on the Metasploit project, which, if you're at all familiar with, you know the coolness of it begins with shells. I love shells, and there are a lot of reasons why Metasploit is cool. The reason I started using Metasploit is for the shells. It's also the reason I started contributing to Metasploit, because I wanted to get shells that it didn't already know how to get. So I first started in 2008 contributing code back to the project, and I started using it for work, and I started contributing code. I ended up getting commit access through HD and some lucky turns of events, but it's still really all about the shells. And the second major reason I really like the framework is that it's all open source. It's a large open source community, and the community is what makes Metasploit great. Because a lot of people work on it, we get a lot of cool code from a lot of cool people. We get submissions for things that I never would have thought of. And we get techniques that just come out of nowhere from somebody who thought, hey, this is a cool idea, I'll write it for Metasploit. An example of that is Railgun, which if you've ever done any kind of post-exploitation, Railgun is how a lot of our post modules are implemented. It's basically a direct interface to the Windows API from an interpreter session. So you can call Windows API functions inside Ruby that happen on the remote target. And that came in from a guy who just sent us the code, dropped it in our framework mailing list, and then I never heard from him again. So we get a lot of awesome code with a lot of awesome ideas, and it could be Black Ops, I don't know, like whatever. It's cool code, I'll use it. Because it's BSD licensed, you can use it for whatever you want. You can modify it, you can change it, you can distribute it, you can obfuscate it and sell it as something else. Take our name off it if you do that. We might get angry if you start selling it, and we'll have words, but it is BSD licensed, so most things are completely legit. It's really easy to write your own stuff, and because Ruby is easy to learn, it's especially easy to write Metasploit modules. We go to great effort to make modules less painful than learning how to be a programmer. So if you've never written any code in your life, reading a couple of Metasploit modules can jumpstart you into writing code for Metasploit that is considerably easier than learning how to be a professional developer. If you've ever scripted in any other language, you can pick up Ruby in an afternoon. At least the important bits that you need for writing a Metasploit module. So open source makes that happen. Open source allows for all of that stuff. And we're now, as you can tell by the logo there, we're hosted on GitHub. So it's especially easy for you to just go on GitHub, create an account, it's free, clone the repository locally, make your changes, and if you want to submit your code back, it's really easy. You just push it back up to GitHub, and you send a pull request. Somebody comes and reviews the code, and we land it in the trunk, and then now your code that does your cool technique that nobody ever heard of before you thought of it is in something that has a user base of 150,000 people. So you go from never having published anything before to having a whole bunch of people being able to see the cool thing that you just did. Another great part of Metasploit is that Ruby is a lot easier to write than C. The advantage, of course, is you can learn it more quickly. You can write it more quickly. You don't have to worry about memory corruption crashes when you forgot to free that thing and, oh, hey, give somebody a shell, by the way. We'll talk about this more in a minute, but suffice it to say that Ruby saves you a lot of time. You know, sometimes you need to hand assemble a payload and, you know, make sure that all of the bytes are exactly what you need because you have to be very precise. But most of the time you can save a whole bunch of headaches, a whole bunch of effort, and a whole bunch of time, a whole bunch of typing by using Ruby. So why privilege escalation? I assume that since you're here, you're interested in privilege escalation, so you probably know why you want to escalate your privileges. It should be fairly obvious. If you're... someday you might want to be a unicorn, and then you can be like Dave Kennedy. Thank you. I'm just gonna leave that there for a second. So, I'll give you another shot. There you go. Tweetord. So high is better than low in general. You want more access to more things you can do. You have more options for persistence, for stealth, for the cool things you can do. You can sniff packets, you can do all kinds of cool things. If you're root, if you're not, then it's going to be more difficult. You can do some really interesting things with memory injection and all of the debugging APIs available. In Windows, there's a whole series of functions that probably shouldn't exist. The read process memory, write process memory, create remote thread, all of those functions are intended ostensibly for debugging, but debugging is also a great way to steal shit. So if for example some service takes a password and it stores it for something, hangs onto it for a while, doesn't clear it out of memory, we can just go in and root through its process space, steal that out of memory, and all that's available because of the debugging API. Without that, you can't steal things as effectively, and we want to steal all the things. So you need root for that. If you want to do the super cool injection stuff, if you want to steal things out of memory, you want to sniff packets, all of that requires root. So here's a quick contrived example for Linux. Very simple, just set UID to 0, say I'm going to be root, and run bin sh. And the reason we need to do that is modern bash, modern iterations of sh, all drop privileges if their effective UID is not equal to the real UID. And when that happens, like if bash itself is set UID, then the real and effective will not be the same, so it'll drop privileges and you don't get a real root shell. So to get around that, we make this quick little executable that's just a wrapper around sh that doesn't drop privileges. And this is essentially a root elevator. It turns out that root elevator is actually a tool that they use to break up teeth. So this is a dentistry device used for breaking teeth, and it just doesn't seem cool. I don't know. Anyway, so to do this in Metasploit, we start with the exploit local module type. And that's a relatively new, fleshed out module type, but it's really been around since the beginning. Exploit remote is the one that everybody uses, and we've got, you know, almost 1,000 modules that are exploit remote. Exploit local has always existed, but it didn't really have any sort of functionality. In the last couple of months, I've added the ability to use all of the normal post API that you're used to for creating post modules in addition to some of the useful things from exploits and tying those two together so that you can, for example, create a payload as an executable and then write it to the disk on the target and execute it. And all of that is very simple with the new API. The exploit mixins provide a payload and a handler, and so you get all of the same normal console options that you're expecting as a user. You set your payload to Windows, interpreter, reverse, TCP. It's all the same stuff, and it sets up the handler for you automatically. So if you're familiar with some of the post modules that previously implemented some of this functionality, like persistence is still around. Eventually that'll get all of the post modules that take a payload will get migrated into new local exploits. But if you're familiar with how the post modules work, they have sort of a kludgy way of dealing with payloads where the module itself builds its own payload and then converts it to whatever format you need. With exploits, it's a lot simpler because that functionality is already built into how exploits work. So it's just a few API calls instead of dealing with building your own payload and all of the itinerant crap that has to go along with that and setting up payload options and everything. So you can include exploit mixins and post mixins, which also gives you the ability to for example, modify the registry, write files, read files, in a platform agnostic way for the most part. So obviously, registry manipulation only works on Windows, but the write file API, write file, read file, append file, download, upload, all of those things are platform independent and should work basically everywhere. With a couple of caveats, shell sessions on Windows typically are not binary safe because CMD really, really sucks. So here's, for our previous contrived example, this is our contrived exploit. So I just talked about the exploit mixins and the post mixins, so we include the things we need. We set up a platform to be Linux and an architecture to be x86. So this is exactly the way normal remote exploits work. They do all of the same stuff. So then our exploit method, again, is really simple. We're just generating an executable. We're writing it out to a file. We're marking it executable. And we run it with temp.sh, which is that setuid wrapper that we have around bash. So that particular example is really the guy who set up that setuid wrapper. He's shooting himself in the foot, kind of intentionally, because you know what's happening. There's a real-world example with Nmap. Now, I'm sure everyone in this room is familiar with Nmap, but have you ever read the man page where it says, never set UID root the Nmap executable for security reasons? That's all it says, for security reasons. Well, did anybody ever look at what those security reasons might be? So, also, users of Nmap all generally know that Nmap works better if it's root. They also occasionally run it setuid to save themselves from having to sudo. Saves themselves a little bit of time, but it gives us an avenue of attack. This is not the default configuration. It's really stupid, and the man page tells you not to do it. And as a result of finding this, well, a friend told me, hey, I found setuid nmap on a couple of boxes, and hey, it's awesome. I looked into why that might be stupid, and it turns out that you can have Lua scripts for the Nmap scripting engine. NSE is super awesome. If you want to do any kind of advanced scanning for higher level protocols, you want to dig into this XML piece of blob that came out of this thing that's on an HTTP server. Lua makes that really easy in Nmap. So if you're interested in fingerprinting and potentially pulling out really cool data from some network service, NSE gives you a quick way to do that. But for our purposes, it also allows us to run Lua code as root. It has a specific structure, so we need to take that into account when we're writing the exploit. So it's got to have an action function. It's got to have a pre-scan, a post-scan, a couple of other attributes. So it's got this structure, so when we're writing our exploit, we have to take that into account. But it turns out it doesn't actually care. It will evaluate it anyway, even if it doesn't match the structure. It'll evaluate it, find out that it's not valid for its regular structure, and then just discard what it did. And in this case, what it did was os.execute cmd. And cmd is the payload we created. So from Metasploit, we can write the NSE file out onto the target, run nmap with -- script, and give it a path to that file. And in older versions, in the 5-something days, the scan wouldn't look at your script unless you actually had a host for it to scan. On 6, it will. So if you don't give it a host, it'll still run the NSE. On older versions, it doesn't do that. So to force it to read that script, we give it a host of : : 1 just because it's short. In the real module, it actually uses 127.0.0.1, but it didn't fit on the slide, so there you go. So here's a quick demo. Should be very simple. Hopefully it'll play. There we go. Okay, so just like running any other module in the framework, you've got your options. For exploits, you also have a payload. Like a post module, you also have the session option, and that will be the session you want to exploit with this module. So you can see in this, when I run sessions the first time, I drop into the first session, I have UID 1000. You don't see anything. Well, it's awesome. Can we make that go over there? Can we go over there? Maybe? Well, hey, something's happening. Something, eh? And go. Aw. Okay. Zoom? Sure. Maybe. Oh, hey. Okay. All right. So I'm going to do this backwards. All right, so the first session here is UID 0001. So now we upload the NSE file. We chmod everything correctly. And we've got our new session, and it's root. Who doesn't love root shells? So then you do the root dance. The Scalevator bug, there was a 0-day in that was used by Stuxnet. Josh Drake actually wrote this exploit. I'm just mooching off of him. The task scheduler stores XML files or stores tasks as XML files. So it's just this, very clear format that you already know how to parse. It's readable and writable by the user that created the task. which sort of makes sense because they created it, so they should be able to do stuff with it. The downside is that it uses CRC32 to verify the integrity. So you can, so Windows will verify that it hasn't been tampered with, quote unquote, because the CRC32 matches. Well, it turns out that's actually really easy to brute force. So schedtask.exe is the command line thingy for making tasks. So this is part of the exploit. You just create a new task with a random task name, and CMD is the thing you want it to run. And in this case, it'll be some executable. So here's the rest of the important parts of the exploit. We changed least privilege to highest available, because why not? And we changed whatever the user ID is, which will be your user ID. It'll be some SID right there. We change it to the SID belonging to anybody? Anybody? System. Thank you. And then we find a CRC collision. Okay. And once we've got a CRC collision, then we can write that file back, and Windows thinks that everything is perfectly legit. So the CRC matches. This must be a perfectly good task, so I will run it. And oh hey, it wants to run a system, sure, and it wants to run this command, all right. And then you do the root dance. So remember how I said Ruby is better than C? Most of the time that's true, except when it isn't. A lot of times, like things like that, you can just write out a file and tell something to run it, and it runs it as root for you, and you just win. That's awesome, but it doesn't always happen that way. So sometimes we need to compile. And Metasm is the Ruby way to do that. Metasm is an amazing project by a guy named, I'll just go with JJ because I can't even begin to pronounce his name. It's a completely pure Ruby compiler and assembler for x86. It'll compile C for x86 and x86-64, and it will assemble assembly language for a whole bunch of stuff. And in fact, he's even working on an assembler for Dalvik bytecode, which is pretty badass. The compilation always produces dynamic executables. There's no way to combine .o files right now, but most of the time that's okay. You don't really care too much about static executables. You can do pretty well with dynamic. You can create shared objects though, and that'll be important for another exploit we'll see in a second. The process right now, and you can see there's an asterisk there because this is subject to change without notice. I'm still in the middle of finding the right way to do this API. I've gone through about 3 iterations right now and found 3 different ways that it sucks. So this API will hopefully get better as we write a few more exploits using it to figure out the best way to write C in Ruby that compiles to shellcode. So I know that it sucks, but everything is awesome and nobody's happy. So we'll just go with that. Right now, the process is you must develop on a system with C headers. So if you're talking about Linux, that's got to be you've got to have libc headers. You have to have socket.h and all of that sort of stuff. You have to have unistandard.h. And that gives you all of your structs, all of your pound defines, and everything you need to pull the imports from libc on the target. As I said, it builds dynamic executables, so you have to use their libc on the target. With Windows, you need basically the Windows headers from some compiler. Visual Studio has everything. So you just set the proper load path to include the Windows headers from Visual Studio, and it compiles an executable for you, or it compiles shellcode, which is just the most amazing thing ever. If you you write your payload in C, and it compiles it down to shellcode. That's awesome. So here's the exploit that I was just talking about. The first iteration of this exploit doesn't actually use a compiled payload. It uses a simple executable, or excuse me, a simple command. You can compile an executable from whatever payload you're using instead of using like a command shell payload. You can use an executable by writing it out as a file and calling that as your command. There's another exploit technique for this bug that allows you to use a shared object that gets loaded in the context of a root process. So we'll get to that in a second. The bug itself is that udev gets events from the kernel, and that's how it figures out when a new device has been added or something has been removed. So when you plug in a USB drive, udev gets an event, and that event comes from the kernel as a multicast netlink socket thing. So the kernel writes some goo to a netlink multicast socket, and any process that is listening for that particular multicast group will get the event. So udev listens for all the events that it cares about, and the kernel sends the goo that tells it what's happening. It turns out that you can also send it unicast requests, or unicast goo, which can happen as an unprivileged user. Then udev doesn't actually verify where it came from, so you can say, hey, I just created a new device, or hey, I just removed a device, whatever you want to do. When this bug first came out, the discoverer was, I believe it was Julian Tynes and a couple of other guys working with him. Crow.org is the blog. They hypothesized a couple of different ways of exploiting this, and I think that process is really interesting. So you have the ability to tell udev that there is a new device, and it can do things based on that information. You could say, hey, I have a new device. It happens to live at dev SDA. And it'll say, okay, you've got a new device. And I say, okay, as part of that, I want you to create a new directory that points to that, and that'll give you raw block access to dev SDA. So you could do that, and then using your raw block access, go dive down into that disk, find something interesting, and change a bit to turn it set UID. That sounds really hard, but it's totally cool. But again, hard. So easy is better. The better solution is 95 udev late.rules, which is a rules file that ships with most relatively recent, at the time of this bug, udev Linux distributions. The important part is that last bit there, where it says run plus equals env remove command. So it takes an environment variable, which can be set from that udev goo, from that netlink goo. It takes an environment variable and adds it to the run variable. And run is a special thing that udev uses. When it's done parsing all of the rules, it runs everything in the run variable as a command. And again, udev runs as root. So the bug is relatively simple. You just run this quick, you create the thing that tells it that this is the environment variable we need. We set remove command to be some executable that we've written, or some command that we want to run as root, and we win. So the goo that you need to do that is this. It's relatively straightforward. The whole idea of it is run my evil, temp evil right there. And of course that can be randomized, and in the actual exploit module it is. But unfortunately, 95 udev late rules only ships on some things. So some of the older distributions, where you can still get a shell because it's vulnerable, they don't have that rule, so you don't have a quick way to just run a command. So the other option, because the this blob of goo can also set other environment variables. You can set LD preload. Then you write out a .so file, and any of the commands that run will give you a shell. So something will happen after it parses all of these things. It'll run a command. That command will use your LD preload. It loads up your .so. So then your constructor runs as part of that executable. I'm still working on that for 64-bit, but I have it working in 32-bit as of a couple of days ago. I've been running like crazy to get ready for DerbyCon, so I haven't committed that to trunk yet. It'll be there in the next few days. So the cool thing about that is this is all you need to compile C. C parser is, again, one of those things that might change at a moment's notice when I decide that the API sucks. cparser.parse takes main here as a variable, and main.c is just something to call it so that it will give you proper file name with a line warning in case there's a syntax error or something along those lines. So main in this case is the C necessary to generate that goo we just looked at. Then we create a new compiler. We compile that down and parse it. Then we assemble what it parsed down to. Then once we've assembled everything, we encode it as a string. And in this case, it's encoded as an ELF file, so we can write it out as an executable. You can also write it out. You can also encode it as shellcode instead of an ELF, and it also has several other kinds of executables: AOut, cough, PE, a bunch of others. But this is the entire process necessary for exploiting that bug. Once you've got the C necessary to create that goo, there's another step here for the LD preload version, and that's going to entail creating a lib, like I said. So we do this same process, but for some C code that runs our shell code. So we create a C wrapper that allocates memory, sets it to read, write, execute, puts the shellcode in there, and jumps to it. So a relatively simple shellcode harness that you'll use a lot if you're developing a payload. The same thing applies when you want to run it in a weird situation, like this, where we're in an LD preload.so file. So we just compile it down, we turn it into an SO, we write it up to the target, we run it using the udev exploit, and then we delete the whole thing when we're done. So something that was relatively complex, this is, I mean, it's a fairly simple bug, but requires a lot of steps. If there's no compiler on the target, and all you have is the existing C, you're kind of screwed. With the Metasploit module, you don't need to have the headers from the target because you can use local headers, and because of the way Metasm does its symbols, it is more portable than GCC. GCC uses versioned symbols so that it doesn't have mismatches in API changes. They are very, very conservative in that. It's not necessary to be so conservative, especially when most of the time all you really need is going to be like mmap, printf, a few others that are important. Whatever is required to trigger your bug. Often you'll need the socket stuff, socket, bind, listen, accept, connect. Those are generally all you'll need. Most of those can be proxied directly into syscalls, so in some cases we can just skip libc altogether. And then it doesn't matter how different your version of libc is versus the version on the target, whereas you'd be stuck if you had to compile it with GCC. So using Metasm, we can save ourselves some headache and potentially prevent ourselves from losing shells. So the next bug is sock send page. This one's interesting in a different way. We're still compiling C, but send page is a kernel bug. So it's a null dereference, and this is an awesome bug because it affects every kernel from late 2001 to 2008. Or almost 2009. So sometime in 2009. So it's 8 years of 8 years of kernels. Every single kernel is vulnerable to this bug. it's a simple null dereference, and if you've done any user mode exploitation or any remote exploitation, null dereferences are hard on user mode. You know, if you get a null dereference in Flash or something, you've got to be marked out, right? Null dereferences in user space suck. They're usually the kind of bug where the stars have to align and you have to really know everything about that process before you can get a shell. In kernel mode, you just put shellcode at 0 and you win. It's awesome. So Linux allows you to mmap null, which means I want to use the page of memory at 0. And then you just put your shellcode there and trigger the bug, and it runs for you in ring 0. Now, ring 0 provides a few simple facilities, but not a whole lot else, because now you're running inside the context of the kernel. You don't have access to syscalls. You can't call a syscall because you're in a syscall. So there are more caveats involved with kernel payloads. We have to be really, really careful not to break, because if you crash IE, for example, you know, maybe you get a crash report, but nobody cries about it. If you crash in your payload in kernel mode, you get a panic. The whole box goes down. You get a blue screen, you get a panic, and that's never a good thing. Not only did you, by triggering a panic, not only did you just lose your shell, you also tipped off whoever's sitting there, or if it's like a production server or something, you just cost somebody money. And when you cost people money, they usually don't want you to do very well. Just a tip. They will not be celebrating your successes. So ring 0 shellcode is fairly well documented now that several people have put a whole lot of effort into creating reliable ring 0 shellcode for Linux. The most public is Spender's Enlightenment framework. Has a big chunk of ring 0 shellcode that can save you a lot of time by abstracting out the problems with ring 0. So less than 2629, so before 2629 was released, creds were stored in a task struct. So what are the process of getting a root shell after you get ring 0 code execution? You have to find something interesting in the kernel that will raise your credentials. So we need to find where your UID is stored, basically. Then we need to make sure that that's actually the right place, because if we just start writing zeros to random spots in memory, you're going to have a bad time. So we need to find where our process lives that stores the UID. We need to make sure it's the exact right place. Fail gracefully. Just bail out if you don't have the right place. It is much better to maintain a low privileged user shell and not crash anything than it is to cause a seg fault in kernel space. Please, please don't do that. So then we need to change those bits, and we need to get back into user space gracefully. In versions less than 2629, we can just scan for a thing that looks like a process, which will be a 0, which is your current runnable state, and if you were currently executing, then the only possible state is runnable, which is 0. So you find a 0 followed by your UID 8 times. So that'll be your UID, your effective user ID, etc., etc., etc. You're stored, you're saved, the others, a couple others. Then the GID after that. So those are known values, so it's really easy to fingerprint. You can get them in user space before you start. So you find your UID before you start the exploit, you trigger. So now you're running in ring 0. You find your 0 followed by your user ID 8 times. Then you change that user ID to 0 8 times, and you return back to user space. In some situations, that's not enough. Capabilities also can make your shell less useful. So the capabilities come after your UID and GID, so you have to set all of those to 1s. There's a lot of nuanced stuff with how capabilities work, but the general idea is if you just set them all to 1s, you win. So let's do that. With kernels 2629 and after, all of that changed. So now instead of having your UID in the same struct as your your task struct, now they're their own separate structure, and you can't nearly as easily just grep through memory until you find the right thing. Fortunately for us, because this is now difficult for regular kernel developers, they have to have the same way to do this too, some way to do this too. So the kernel exports 2 functions: prepare kernel cred and commit creds. The simple way to get them is just ask proc k allsims, which is available most of the time. The only time it's not available is with hardened grsec kernels. But in other situations, it's pretty much always available. So you can just pull out the symbols from there, find out the address of these functions, and call them just like the kernel would. So you create a root credential and commit creds, which stores them to your current process. So you just find these 2 functions, you call them, and you win. So we're going to try this one more time. And nailed the dismount. Okay, so kernel exploits are always a little bit scary because they're in the kernel and there's always the potential that something could go terribly, terribly wrong. So I made a video. And you can see here, again, I'm a regular user. I can't see though, so I'm gonna come over here and look from the back. You can see I'm a regular user with a big UID, much bigger than 0, which is a bummer, so let's fix that. We set the session to the appropriate thing, then we compile all of the files that we need to produce this binary, we push it up there, and we get root. Woot. Where is my mouse now? Oh, okay. And then we do the root dance. Carlton's my hero. And then, how much time do I have? 5 minutes. Okay. So I've got some leftover junk from DEF CON that I'm just going to run through really, really quick. SMB relay is old school. It's super cool. You'll get a lot of shells from it. This is how it works. Attacker, victim talks to attacker talks to a target. Target sends back a challenge. So we pass that on to the victim sends it back to the attacker, we relay that again to the target, and now we're logged into the target. So what does that mean? Now we've got credentials from the victim to the target, and we can do whatever the victim can do on that target. So SMB relay is a well-known attack. MS-08068 fixed it for the simple case of reflecting directly back to the victim. And so it basically fixed it for coffee shops and airports. But you can still relay, to this day, you can still relay to another server somewhere else on the network. And it'll probably be that way for a very long time. There's some mitigations that make it go away, such as mandatory signing on everything, makes it difficult. But for the most part, it's going to be around for a long time. Quick little awesome sauce technique, mostly that I stole from Rubik's, but an LNK file can have an icon. An LNK file can have an icon. It turns out a lot of things can too, but LNKs are especially easy to build and drop. So we create an LNK file we put it on a file server somewhere, like some Scratch file server that everybody logs into sometime. Eventually, someone will open up the folder containing that LNK file, which has an icon. That icon can be a UNC path. The UNC path points over to some compromised host that you're using to run SMB relay. So from that point, you don't actually have to compromise anything that a victim normally talks to. You can compromise some server that they never ever see and relay it over to another target, and you win. So all of this is possible because of automatic domain authentication. Windows stores creds in memory. Like you're probably already aware, hashdump can pull them out, but you can also do other GUI things, and all of that happens transparently. So you open up a file share that your user has access to. All of that happens transparently. The reason for that is automatic domain authentication. So we can take advantage of that as well. If we're on a compromised machine and our user has local admin on any other box, in most cases we can also create services on that box. Well, services can also be UNC paths. So again, we don't have to have a file on that target. We can fire up a share on the compromised machine, have the victim that we want to shell on call back to us to get the executable, and now not only have we done essentially the same thing as PSExec, but we've done it internally through a pivot on a compromised machine. And the bigger advantage is we've reduced the forensics footprint. Now we only have our executable living on the one compromised machine that we started from. We don't have to actually upload it to the victim that we're trying to get a shell on. And since we don't have to do that upload, there's much less forensics footprint going on the network. So we can do all the things. So that's a scanner now. And all of that happens because of the ability to open SC Manager, which is the services controller manager with a machine name. So you tell it, I want to open that box's service manager. And Windows will let you do that if you have local admin on that target machine. Again, all of this happens transparently. So if you're a user running as, so my interpreter shell is running as your user has local admin over there, I can open that and create services. I don't need a password, I don't need a hash, I just win. Binary name again can be a UNC path. I think I'm going to skip the demo because I'm out of time. I want to, for the future, I want to be able to compile shellcode, push it up to memory, and run all of this stuff in memory. That's going to be a little bit easier in Windows because Windows already has stuff for the get system command that Stephen Fewer added about a year ago, maybe a year and a half ago now. So there's already some stuff for compiling the shell, so there's some stuff for running shellcode inside a interpreter process. I want to also do that as transparently as possible for Linux as well. Then we do the root dance. I want to take everything that's in post, all of the architectures, all the platforms, escalate. I want to take all of those privilege escalation. They're essentially exploits. I want to move them into exploits and make them real local exploits so they have all those same payload handlers and everything. I want to take some of the code in the small handful of compiled C exploits, pull that up into mixins so that you don't have to deal with any of that library stuff. So writing a kernel exploit is just triggering it, and that's my plan. It may take me a while, and I would love to have some help with that if any of you are interested in working on it. So shells are awesome, root shells are better, Metasploit is awesome, and it gives you more stuff. And these are a couple of random images that came from my Google searching while trying to find funny things. So, any questions? Robot monsters. I don't know, disco. No questions? Feel free to hit me up on email or Twitter. I'm always in #Metasploit on Freenode. And also, one last image. It turns out when you Google getting higher privileges, there's a movie called Pot Zombies, and I don't know. I mean, What? Yeah, when they get the munchies, it's your ass. I don't. What is this? I don't even. Okay, I'm done.